guys, welcome to this page of the notes. And what I want to do on this page of the notes is talk a little bit more about imaginary numbers and just kind of introduce this idea of the imaginary number system. And here's the way it's going to work. All of the example problems that we did on the previous page of the notes, you'll notice was just a number with an I, right? An imaginary number, what we call a purely imaginary number. 8i, plus or minus 3 times the square root of 2i, right? There were a bunch of other ones here. That's not the only way that these numbers are going to show up, though. And for example, I give you one right here where you have 2 plus 3i. What we've got here is the real number 2 at the beginning, and then the imaginary number 3i at the end. And when this happens, when we have a real number and an imaginary number, we call this collectively a complex number. So actually what we're talking about here is the complex number system and we call it a complex number, right, because it's a combination of both real and imaginary numbers. And here's the way it's going to work. What'll happen is anytime right here. Anytime the general form for complex number is a plus bi, where a is the real number and bi is the imaginary part of the number. Now, to get a real number, what happens is my coefficient in the imaginary portion of my complex number is going to be 0. Well, 0 times anything, of course, is 0, and what I'm left with is just a, which is a real number. So anytime you guys are using real numbers like 4, or the square root of 3, or pi, 10, minus 16, those real numbers are complex numbers where the imaginary part of the number has just gone away because b was 0, that leading coefficient was 0. Now, vice versa, what's going to happen here in a complex number is if the real part of the complex number is 0, so example, again, I've got my complex number, a plus bi, but now if I make the real part of that complex number, a, if it's 0, it drops out, right? And I'm left with just the imaginary part of the number, just left with the bi, which is a purely imaginary number. So here's what you've actually got, guys, kind of a broad overview of the way our number system works. Is you've got sort of over everything, right? You've got the complex number system, right? That's what there is as far out as you can go. You know, sort of the 30,000 foot view is complex numbers. And then you can begin to break it down from there. From that complex number system, if b is 0, you jump into the real number system, which is what you guys have been using since elementary school. When b is 0, that imaginary part drops out, and you guys are now in the subset real numbers, which you can do all kinds of amazing things with. But if b is not 0, right? When b is not 0, you now move into the imaginary number set, right? So overall, you've got these complex numbers, and what you guys have been doing since elementary school, all the way up through Algebra 1 and geometries, you've been dealing with complex numbers where that b was 0, the imaginary part goes away, and you're just left with the real number. What we're now going to do here in this section is no longer assume that b is 0. We're now going to deal with complex numbers where that b is not 0. And you have imaginary numbers, or what we could also call these complex numbers, as long as there's a real part in that complex number. So that's what we want to take a look at, and we'll do so here on the next page of the notes, where we're going to take a look at that first objective we had, performing operations with complex numbers. So here's the way it's going to work, and it certainly is not, I know it sounds scary, I promise you it's not. They actually work very similar to the way that real numbers work. So here's what we're going to do. My first definition here is the equality of imaginary numbers. And I give you kind of this book definition here, but really all you guys need to know is just this little bit right here. In order for two complex numbers, a plus bi, right, that's a complex number, to be equal to another complex number, c plus di, well, that only happens if and only if a is equal to c, so the real parts of the complex number have to be the same, and b is equal to d, right? The imaginary parts of the complex number must also be the same. And guys, this should make perfect sense. The only way that real numbers can be equal to each other is if they're the same number. Complex numbers are no different. The only way that two complex numbers can be equal to each other is if they're the same number. So let's go ahead and take a look at how I might ask you to do one of these problems on a test or a quiz, or even in the homework. I have given you, I want you to find the values of x and y that make these complex numbers equal to each other. Please notice, right, I've got a complex number here. So we're looking for the values of x and y that make these two sides of the equations, these two complex numbers, equal to each other. Well, based on my definition, which was right up here, the only way that two complex numbers can be equal to each other is if the real parts are equal and if the imaginary parts are equal. So that's exactly what I am going to do. I'm going to take the real parts of this number, which is going to be the 3x. Actually, you know what? Before I do that, let me distribute my I through the parentheses. Let me do that first so that I don't have to worry about it later. So I'm going to have 3x minus 5 plus yi minus 3i is equal to 7 plus 6i. Awesome. Okay, now I need the real parts to be equal to each other and the imaginary parts to be equal to each other. So we're going to kind of split this problem apart into the real, the imaginary, and then we just make sure that we have equality between those two sides. So here's what I've got. As far as the real numbers are concerned, I have 3x, which is a real number, right? 3 is a real number. X is just a variable that represents a real number, even though I don't know what it is. We're going to solve for it. I have a minus 5. Obviously, minus 5 is a real number. Y, well, I don't know what y is, but it's with this I, which means that that's an imaginary number. And this 3i, so that's imaginary. So that takes care of everything on the, for you guys, what would be the left-hand side of the equal sign. On the right-hand side of the equal sign, my real number is 7. The 6 is not real because it's with an I. That makes it imaginary. So I have a 7. And we would go ahead, right? These have to be equal to each other. So let's go ahead and solve for x. 3x is equal to 7 plus 5, which means that 3x is equal to 12. Divide both sides by 3. I get that x has to be equal to 4. So in order for my original equation to be equal, I need x to be a 4. Which makes perfect sense, right? 3 times 4 is 12. 12 minus 5 gets you 7. I wind up with 7 over here and a 7 over here. Awesome, it checks out. Now let's take care of the imaginary part. Again, remember, my definition says that the imaginary parts must also be equal to each other. Well, let's take care of the imaginary parts. I have a yi minus 3i, and that's all equal to 6i. Well, I don't know what the y is. I'm trying to solve for that. So let's go ahead and add the 3i to the other side. And I know you're probably looking at this and going, what the heck am I supposed to do with that? I don't know what to do with imaginary numbers. Guys, it works the exact same way it would combining like terms if I were a variable, right? 6i plus 3i will just simply be 9i. Works the exact same way as it does for real numbers. So yi is equal to 9i. And to get the y by itself, I divide both sides by I. Sorry, I'm going to have to squeeze here a little bit. I have 9i divided by I. And yeah, just like it would with real numbers, if I were any other type of variable, I have an I in the top, I have an I in the bottom, and they cancel each other out. We get y is equal to 9. And this should make sense. If I plug a 9 in for y, 9 minus 3 is 6. And 6 times I gets you 6i. So by plugging in a 4 for x and a 9 for y, this side of the equation becomes 7 plus 6i, which is exactly what I was given on the other side. Let's go ahead and try one more of these. We'll go a little bit faster on this one now that we kind of understand how it works. We got to split the real and the imaginary parts up, but let's go ahead and take care of those parentheses first. 5x plus 1 plus 3i plus 2yi is equal to 2x minus 2 plus yi minus 6i. The real parts are going to be 5x plus 1. The 3i and the 2yi are imaginary, so I can't include them with my real numbers. So I go to the other side of the equal sign, where I have a 2x and a minus 2. All right. Well, let's go ahead and solve this. You got to get the x by itself, so we combine like terms. Subtract the 2x to the other side. 5x minus 2x is equal to a negative 2. Subtract the 1 to the other side, and we wind up with 3x is equal to a minus 3, which means x would have to be a negative 1. Okay, let's take care of the imaginary part. All right, well, on this side I have the 3i and the 2yi, and that's all equal to yi minus 6i. Well, again, let's go ahead and get the like terms together on the same side. I will, let's see what's going to be the best way to do this. It looks like the best way is going to be to, I would subtract yi to this side and subtract 3i to that side. So that's what we'll do. We'll do 2yi minus a yi is equal to a negative 6i minus 3i, and go ahead and combine your like terms. 2yi minus 1, right? There's a implied 1 in front of that I. Well, that just leaves me with yi. And a negative 6i minus 3i should be minus 9i. Once again, I got to divide both sides by I to get that y by itself. Those i's will cancel each other out, and I get y is equal to a minus 9. And so there we go. What you've done is you found the value of x and the value of y that would make both sides of, or cause these complex numbers to then be equal to each other. Guys, thanks for joining me on this page of the notes. Head on over to the next page, and I'll meet you there.